Hi, everyone. Thank you so much for joining us for a special guest speaker session at the Regional Asia. We have with us Weijia, Shi, and Han. Weijia is a PhD student at University of Washington. Her research focuses on language model pre-training and retrieval-augmented models. She also studies multimodal reasoning and investigates copyright and privacy risks associated with language models. Han is a research scientist at Metafair. He recently completed his PhD at University of Washington and his work focuses on multimodal generative AI. Thank you so much, Vijay and Han, for taking out time, and I'll hand it over to you.
Thanks so much for the introduction, and thanks everyone for being here. So in today's talk, I will give a broader overview and how I think about what kind of language model we should build in the future. So instead of just focusing on like one project, the LMFusion, I will give a broader picture covering several projects. In general, I will dive into some of the challenges we're facing with current language models, and I want to convince you that simply scaling up the current paradigm is going to hit a wall, and I will propose an alternative way to build this model. So this may not be the only way to go, but just want to offer a different perspective. And please feel free to post any question online. I will check it. I will check it. I will check it during the talk, and we also have a QA session at the end. Okay, cool. Let's get started. So a default paradigm for today's language models looks something like this. So we train one very large model end-to-end on all data, and this one model is deployed for every use case. We've seen a huge success just by scaling up this monolithic model. As we increase the model size and amount of training data, they just keep getting better and better. And the compute required for training these models grows exponentially. But at the same time, we're also seeing a lot of limitations with this monolithic design. For example, once a model is trained, it becomes very difficult to update the model with new knowledge because all the data and knowledge are deeply intertwined within a single set of parameters. But there are many reasons we may want to update the model. For example, in our previous work, we found it's possible to detect pre-training data from current black box language models. We apply our proposed approach to detect the GPT-3 pre-training data, and we found that model is likely trained on books listed here. And a lot of books are copyrighted from the book 3, the pirated books collection. And at that time, the book 3 dataset was posted online. So it's possible that the model developers just scraped the entire internet and accidentally included in pre-training. But including this kind of data in pre-training could lead to a lot of problems. Like many book authors filed lawsuits against the major AI companies, requesting their data to be deleted from the trained models. So this raises a question. Is it possible to actually remove the data from a trained monolithic model? Researchers have proposed different unlearning methods with the goal to remove specific training data from a trained model without hurting the model utility. Can any of these methods work in case like this? In our subsequent work, we found it's actually very difficult to this unlearning method to use this unlearning method to make a model forget specific data. So looking at this plot, ideally, we want the model to fall in the top left corner. So it will preserve the model utility, but makes the model forget the target data. But for a lot of unlearning methods we evaluate, they either remove the data completely, but at the cost of utility, or they cannot really make the model forget the data. So for the points lies in the middle. So this shows it's very difficult to remove unwanted data from a monolithic model once the model is trained. And not just hard to update the current monolithic model, the current scaling paradigm is also going to hit a wall. Data has been very important for driving a lot of progress in model scaling. But we're soon running out of data. So here I'm showing a projection of total stock of human-generated public text versus the data set sizes used to train the major models. You can see if we keep following the current development trend, we will soon use up all data. So we're about to become data bound. We cannot just keep scaling the current paradigm and hope it will lead to the next breakthrough. So how can we do things differently? In this talk, I want to discuss the different principles for building language models. Modularity, not monolith. Building language models from composable components. I will start by giving an overview of what modularity means and explain why I think this is a promising direction forward. There are two types of modularity I will focus on today. The model modularity. Instead of having one model do everything, we can augment it with external modules like retrievers or specialized models. Each bring new capabilities at inference time. And a key example of this is the retrieval-augmented language model. It's a direction I've been studying for a long time, which has also been widely adopted across many real-world applications. So I know many of you are probably familiar with this, but just a quick recap. The way it works is, unlike the standard pre-training models that makes prediction solely based on the input context, retrieval-augmented models would look up an external database, retrieve a few related documents, and combine both the input context and retrieve information to make the final prediction. The data store is very flexible, so you can change it at any time to update the model with new knowledge. I work on different pipelines, at different stage in this pipeline, from building a better retriever model to pre-trained language model to use retrievers. I will dive into the details in the later section. An augmenting language model with retrievers is just one way to add new capability the model does not have during inference. And more recently, I've been exploring how this principle of modularity and of augmentation can extend beyond text to the visual domain. In our recent work, we show by augmenting language models with multimodal tools to sketch and draw, we can make them reason visually much better. Let me give an example. So we have this geometry question, like the angle FEK is 105 degrees, angle BCJ is 105 degrees. Can we find the angle EIC? So I give this question to the previous GPT-4 model, and this is the response the model generates. You can see the model completely relies on text to generate its chain of thought and doesn't get the answer correct. But now I think, how would I approach this problem? So when we solve a geometry question like this, we will naturally sketch it out on paper. We may ask ourselves if a supporting line is needed to help solve the problem. Then we will draw the line on the paper to guide our reasoning process. So this way of drawing and sketching are very fundamental to how we solve the problem, communicate, or even generate ideas. So we let language model do the same thing. Drawing inspiration from this, we recently proposed a visual sketchpad. It's a framework that augments the multimodal language models with a visual canvas and a set of drawing tools. For example, when we're given this geometry question, the model may think, okay, I probably need to draw an auxiliary line, then it use code generation to draw this line. And this intermediate sketch could guide the model to reason through this problem. And we found this ability to think through drawing can greatly improve the model performance on reasoning intensive tasks. So model modularity can address a lot of problems in current monolithic models. But where are we going next? I think we're just at the beginning of this change towards modularity, and we should push it even further. So in this talk, I also want to convince you that the next frontier of modularity lies in data. We should develop language models that are distributed and data modular. So we often say we're running out of data, but to be more precise, it's really the public data that is running out. There's actually a lot of high quality but high risk data currently cannot be used in training language models due to privacy or regulatory issues. So I think one promising path going forward is to find ways to use this private data through new training algorithms and architectures that preserve data privacy. So this brings me to my next proposal, data modularity. Different from standard monolithic models that centralize all data and train all parameters indiscriminately on all of them, I think future models should categorize data based on its provenance, so where the data comes from and who creates it. Then we can train different model components locally on different data sources, preserving data privacy. Then during inference, we can mix and match these different components based on different applications and user requirements, making the model highly customizable. And one example is we can have more fine-grained data access control using this new methods. Let's say if a user have access to a Washington Post and Disney content. In this case, we can turn on the module that train on these two data sets. But at the same time, if another user doesn't have the permission to use any of this data, we can simply turn these components off. I prototyped this idea in our recent work, FlexOlmo, which trains the first mixture of expert language model via data collaboration, letting multiple parties to independently contribute decentralized trained experts. And now this paradigm is being applied within the Cancer AI Alliance to model private clinical records. So this is about FlexOlmo, but what are some other benefits of data modularity? So standard multimodal understanding and generative models are usually trained end-to-end from scratch on the joint text image corpora. So this requires significant computation resources to achieve good performance across both modality. But this method overlooks language models and diffusion models that already exist. So can we in our recent work in LMFusion, we look into the question, can we compose a multimodal generative models from existing pre-trained modality-specific components? So instead of training everything from scratch, can we take existing language model like Llama or existing image generation models like Flux, and we compose them and into unified models with a light fine-tuning? There are many benefits of doing this. So first, compared with the standard model trained end-to-end from scratch, it would be much cheaper to train such unified models because we can reuse the compute of these specialized components. And another benefit is the optimal model size may vary across different modalities. If we just have one monolithic model trained on both modalities, then this means during text generation and image generation, both modality input will go through same parameters. But different modality may require different size of model parameters. So for example, for text generation, maybe we need a larger model size, but for image generation, a small model will be enough. So if we can compose different size models together, then we can also achieve inference efficiency. And the last benefit is because the model architecture is modular, we can easily add another modality component into the final model with cheap fine-tuning. So this is an overview of what I'm going to talk about in today's talk. But in the high level, both like model and data modularity connect to my research goal of developing modular architectures and training algorithms to make language models more controllable, factual, and collaboratively developed. Okay, let's jump right in and talk about model modularity. So in this part, I will take a deep dive into how to build the retrieval-augmented language models. The retriever is probably like the earliest type of external modules used with language models. So many of the lessons and design principles we learned from building retrieval-augmented models can generalize to other types of modules. So I study how to adapt where I study how to build the better retrievers and how to pre-train language model to use retrievers better. Because of time constraint, I will skip the first part. I will talk about how we pre-train language models to use retrievers better. So the standard way to put a retriever together with a language model is to directly concatenate the retrieved documents with the input context and feed it into language models. This works pretty well, but sometimes it still has some errors. The language model has never seen the concatenation of related documents. So oftentimes it will make a lot of errors. So for example, it will ignore retrieval results or rely too much on incorrect retrieval results. So the question I try to ask is, can we pre-train a language model to make better use of retriever? So how would that actually work? Let's think through it together. So suppose we have a large collection of documents in our pre-training corpus, and we pick one of them. So let's say document 0 here, and we will feed this document into the language model and train it to predict the next token, just like the standard language modeling. Now with a retriever in loop, we can take this document 0 and feed it into retriever. Then this retriever would return the top K related documents. So let's say document 5 and document 3 are the top K retrieve results for document 0. And then we can let the language model condition on the both document 5, 3 as 0, just like how the standard retrieval-augmented language model work at test time. But this brings a design question. So where should we apply this loss? So one option is to apply the loss to only document 0 because it's our original target document. But this setup is a bit inefficient. We're fitting in a large amount of context, like both document 5 and document 3 here. But the model is only learning from tokens in document 0. So the training signal is not very rich, even though the input context is long. And the alternative is to apply the loss to all the documents here. Specifically, we can apply loss to document 5, 3, and 0. This setup is much better. It allows the model to learn from a range of context and generalize to conditioning on the varying number of retrieved documents, just like the model would encounter during inference. But here's the problem. So some documents naturally show up more frequently as the top K retrieval results across a corpus. Like in this case, document 5 appears many times as nearest neighbor documents to any other query document. So this would lead to a duplication issue. The model would end up seeing and training on the same document 5 over and over again, which can hurt generalization. So to make training more efficient, we really need to satisfy 2 constraints. The language model needs to condition on a set of related documents, and each document should appear exactly once, preserving its original frequency. And how can we achieve that? We casted this problem into a document ordering problem. So given the pre-training corpus consisting of many documents, we can construct a graph where each node represents each document, and 2 nodes are connected if they are nearest neighbors of each other. And then we can convert this graph into a sequence of documents by traversing it. So in this case, we can obtain the following sequences of documents. In the last step, we just need to divide them into different buckets. So let's say our language model's max sequence length is 20. Then we can directly group the document 0, document 9 together, document 1 through 5 together, and document 7. And once we have that, the training is very straightforward. We can concatenate all the documents in the same bucket and fit it into language models and apply loss to all of them. Now you can see this really satisfies all the constraints we need to meet. So first, related documents are put in the same context. Second, each document appears exactly once. And this method is very simple. All the things I've discussed can be done in the data pre-processing step. So any off-the-shelf training codebase can be used for actual training. So how well it works? We train models with up to 7 billion parameters from scratch on a total of like 300 billion tokens. And we can see our proposed method in context pre-training is much better than the standard pre-training method. Beyond reading comprehension, we also tested how well the model performs when augmented with retrieval at inference time. So here we compare against both standard pre-training and a k-nearest neighbor baseline, which is a version I discussed earlier that is similar to ours, but some documents can appear many times during training. You can see the KN method is not very good, likely due to the duplication problem. And now here's our model. It outperforms all the baseline, showing that training with retrieval can actually help the model read retrieved documents better during inference, leading to around 12.3% improvements. And there are some other benefits our proposed methods can bring, like in-context learning. We also find our methods perform much better on the 32-shot in-context learning tasks. So why does our method also help with in-context learning? My explanation is our training setup helps bridge the gap between how we train the language model and how we use the language models. So in retrieval-augmented generation setup, the model needs to read concatenation of related documents. And in in-context learning, the model also needs to read related example and generalize to a test example. By training the model to condition on the retrieved related inputs during pre-training, we bridge this gap between language model training and use. Yeah, and this method has been adopted as as a training recipe for long context model, because there are not that many long documents out there in the standard pre-training data. So for example, like in Common Crawl, only about 80%, almost about 80% of documents are pretty short, typically under 1,000 tokens, as shown in this figure. So in-context pre-training provides a way to construct long and semantically related context, helping the model to learn to reason across multiple pieces of information within a single long context window. So this wraps up the first part on model modularity. Is there any question in the chat? Oh, yes, one question posted in the chat is, at this point, we will have to assume that retrievers have to be extremely good. Otherwise, the pre-trained models will come out bad. Is this correct? It doesn't need to, I don't think it needs to be extremely good. As long as the documents are sort of related, you then putting all these documents together could provide some meaningful signals compared with the standard pre-training methods. And I'm sure if this answers the question, but by examining the long context documents we retrieved using the enhanced pre-training, we can see sometimes the documents are very related, so it will provide meaningful signal for the next document to conditional. And in another question is, in your model, is the retriever trained alongside the model? No, in our case, we just construct, we do a one-time retrieval and to build this document graph. And the retriever is not trained along with the model. But I think it would be an interesting direction to explore that. But I'm not sure if this will work at the pre-training scale, because here we're doing the pre-training from scratch. If we want to train both things end to end, probably we can apply it to the fine-tuning. Another question is, what were some useful signals that showed you that the model's retrieving abilities improved? Do you mean the training signal or like the evaluation metrics? I think if it's evaluation, we observe like in the long context tasks, our trained model is better, likely because the model hasn't seen a lot of long documents using the standard pre-training method. Okay, the next question is, why not just fine-tune the language model with your technique, and then retriever and language model could both be fine-tuned for better retriever and enhanced learning? Yeah, and that's a really great point. We can definitely apply our method to continue pre-training, but for our experimental setup, we did pre-training from scratch to do a control comparison. And I think do I answer all the question? Is there any more? Okay, if there's no more question, let me move to the next section, the data modularity. So cancer is probably one of the most serious challenges we are faced today. Can we use AI to help advance cancer research? For example, can we train a language model on cancer data, then use it to assist researchers and clinicians in generating new insights or guiding treatment decisions? This is an exciting idea, but there's one critical bottleneck. The cancer data needed to unlock AI potentials already exist, but they are siloed across 57 national cancer institutes due to patient privacy and intellectual property concerns. So we cannot just centralize all the data and train all parameters on them, like in the standard monolithic language model training. So this brings me to the idea of data modularity. And how about we just train different components locally on different sources of data, and then mix-match these components depending on the downstream use cases? There are two key benefits to this approach. So first, we don't need to centralize all data together, allowing the model to be completely trained in a decentralized way to preserve data privacy. And second, whenever we need to update the model, we can simply update the related experts instead of train the entire model from scratch. So how can we build this model? There are different design choices, like what each component is and how to combine them. But in today's talk, I will focus on how to train such model using the modern mixture of expert architecture. So let me introduce FlexOlmo. It's a new type of mixture of expert model where different experts are trained on different sources of data. Before diving into how we design the training algorithm, let me walk you through how the standard mixture of expert works. So here's a head-to-head comparison from our previous OMO-E paper. So unlike the dense model, the mixture of expert model replaces the feedforward layer in each transformer block with a router and a small set of smaller feedforward networks called expert modules, like E1 to E6 here. And for each input token, the router decides which expert to route the token to. So in standard MOE, both the router and experts are trained end-to-end on the entire data set, just like in the standard dense model. So even though the model architecture is modular, there's no control over how specific data influences the model parameter. So we propose FlexOlmo to allow for two features in trainings. So it's a new type of mixture of expert model, but with one key difference: the different experts are trained on different data sources. And our model supports two key features. So first, flexible training. It allows each data owner to train their expert locally, ensuring that raw data remains private and never has to be shared with central entity. It also supports flexible inference. So at inference time, we can activate different experts along with their corresponding data sets based on the end application or user access policy. For example, if the user doesn't have access to Washington Post data, we can simply exclude that trained expert from the final model. So how do we train this model? One straightforward way is to treat each feedforward layers and attention layers as a standard dense model and train each dense model independently on different data source. But this comes with two major downsides. So first, since all the experts, the dense model, are trained completely separately, so no router is learned during this stage. So this means we need an additional merging step to combine all the experts and train the router. And this merging step is not ideal because we need to take all the experts together and do a centralized training. And not just this centralized training, because all the experts are trained completely in isolation, they can diverge significantly from each other, making the final merging very difficult. So to address this issue, we introduced two key training methods. So first, we train the experts to coordinate with each other, and then we design a domain-informed router. Let me explain how this works step by step. So first, we train a shared public model in the first stage, and then this public model is shared with each data owner who use it to train their own expert. More specifically, each data owner would initialize a mixture of experts with two experts. So one is this public model that is kept frozen during training, and then they train their private experts on their local data. We also reuse attention layer from the public model and keep it frozen during training. So this setup ensures that all local experts are aligned with the same public experts. So by extension, they align with each other. So during inference, we can simply combine all the trained experts into one final model. But how does this merging work? And to answer this, let's take a closer look at how the router is trained. In standard MOE, the router is a linear classifier that is trained end-to-end along with all the experts. But in our case, we cannot train the router end-to-end because the experts are trained independently. So what we do is we decompose this router weight matrix W into expert-specific embeddings. So each row here corresponds to an embedding specific to that expert. And instead of initializing the entire weight matrix randomly, like in the standard MOE, we use domain-specific embeddings to initialize them. So let's say our expert 1 corresponds to the news domain. So the way we initialize the router embedding 1 is we take a lot of news article, we feed them into a retriever, and this retriever will give an average document embedding, and we use that to initialize R1 vector. The advantage of using the domain embedding for initialization is that this kind of domain-specific embedding can provide meaningful signals about what type of contents each expert handle, serve as a much stronger starting point. So during local expert training, the public router embedding, RPUB, is shared across all different data owners and kept frozen during training. And each data owner then continually train their own expert-specific router embedding. So R1, R2 to Rn here. Then during inference, we can simply concatenate all the expert router embedding together in the same embedding table. But one thing you may notice here is there's a difference between how we train the model and how we use it during inference. So during training, each expert only learns to route between the public expert and the one local expert. But during inference, the model has to route among all different local experts. So how do we bridge this gap? So we can view this routing as a classification problem. So essentially, during each local expert training, we are learning n pairwise binary classification, deciding between the public expert and the local expert based on the local data. But during inference, we're doing a multi-class classification. We need to recombine all this binary classifier into a single multi-class classifier that can choose among all experts. So the key to making this work is to train each binary classifier in a way that decides decision boundary in a way that decision boundary is pushed as far as possible towards the local class. To achieve this, we introduce a negative bias during expert training to push this decision boundary closer to the local expert. So during the training, the router makes a decision by comparing the score of the local and public experts with the negative bias, so B1 to Bn included. This is how the algorithm works. Let's look at how well it works in practice and some experimental results. So for training our public anchor model, we use 1 trillion tokens from Common Crawl. And to simulate high-risk or private data sets, we selected sources from historically sensitive or have recently become inaccessible data due to the change in data access policy, for example, like Reddit data. So, and we trained 8 experts with a total of 37 parameters, and out of which 20 billion parameters are active during inference. We evaluate the model on both general domain and domain-specific tasks. So let's first look at how each individual expert performs. We find like each expert, like from public to textbook, they are good at in specialized domain. For example, like the math expert performs pretty well on math tasks. On general domain benchmark, most experts perform similarly, but with the exception of the coding experts, which may be overfitted to the coding domain data. Next, we combine all the experts into a unified model using FlexOlmo, and we find it can outperform the best individual experts on their respective tasks. And this is likely because the model can effectively combine the complementary strengths of different experts, selecting the most relevant components for each example in the data set through the router, leading to a stronger performance. We also compare our FlexOlmo approach to other model merging methods like model soup, which average model weights, or other like output ensembling methods like BTM. So across the board, we found the FlexOlmo consistently outperforms all of them. Lastly, we compare FlexOlmo with the standard MOE model trained on the full combination of data end-to-end. And surprisingly, we found that FlexOlmo could still perform better in this case. And compared with the standard MOE, one major advantage of FlexOlmo is its ability to opt out specific data source at the inference time. For example, when we remove the news expert, the performance on the news-related evaluation drops a lot, but other tasks remain unaffected. And this is what we want. It means we can selectively remove a data source without disrupting the rest of the model's behavior. And so now FlexOlmo is being applied within the Cancer AI Alliance to help model sensitive clinical records across different cancer centers. So each hospital will start from a shared public model, then they train their own experts on its patient data. And then these independently trained experts can be merged into unified models. And the data and task is like this. So given the patient history written in natural language, we use a model to predict next clinical diagnosis, future lab values, and missing medications. So here you can see a comparison between FlexOlmo, federated learning, and other open source models. And FlexOlmo performed the best. And it isn't just better than FlexOlmo in terms isn't just better than the federated learning in terms of performance, it also brings several practical advantages. So first, training FlexOlmo happen completely in isolation, but federated learning typically requires synchronization of the gradients across institution. And when we build this federated learning baseline, we actually run into a lot of issues for this synchronization. And unlike federated learning that eventually trains one dense monolithic model, the FlexOlmo architecture could allow for modular updates. So whenever data changes or center changes, we can simply add or update the corresponding aspect without the need to retrain the entire model. So this is about the FlexOlmo. Any question up to this point? Oh, Abraham?
Yeah, thank you so much for the presentation. I was just wondering, how do you train the initial tokenization that's used across all the models? Do you tokenize that's used across all the models?
Oh, you mean the public model here, and how do we train the public model?
The tokenizer particularly that tokenizes the inputs like the data sets into the model.
Oh, yeah, that's a great question. So here we just start from a public open model, existing models, and we give the same pre-processing pipeline to each hospital to make sure the data is pre-processed in the same way. So although the data may have slightly different distribution because different hospital may have different expertise, but I think the overall data format is similar. So we can directly combine the trained experts. We didn't change.
Do you think so why I particularly asked was about the distribution shift, because every hospital is going to have different data sets. So do you think there's anything that could be done to assess how much performance drop you get from the distribution shift?
Oh, whether they can still
like if there's a way you guys are currently evaluating the drop in performance that's coming from the distribution shifts across different hospitals.
So basically what we need to compare is like if we just train one in-house model on one hospital data, does it perform as well as like the combined model trained across all the hospital data? And we found training the combined model across all the hospital data is better than training one model only.
Ideally, maybe how I think a better comparison for me would be if you get a subset of data set that is not from the hospitals, so that's going to be like not clinical data set now because that's won't be available. And then you train on all of those, and then you train individual and you train your experts with subsets of that data set, that seems like a better comparison compared to just training one model with just one hospital's data set.
Oh, I see your point. Yeah, we haven't tried that in our setup, but I think that's a really, really great point. Yeah, yeah, we can definitely add it for.
Okay, yeah, because there are a couple of
Mm.
works that have shown that you can get back the training data distribution by just looking at the tokenizer.
I
Um,
see.
yeah, so I understand that if you train a whole tokenizer across other hospitals, there could be leakage of information. But again, there's going to be a better performance doing that.
Yeah, yeah, that's a really good point. Yeah.
Okay,
Yeah, thanks so much for
that's it.
suggestion.
Okay.
Cool. Is there any other question for this part? Yeah, if not, yeah, let me talk about the LMFusion. So besides merging different text-only components, we could also try to merge models trained on different modality data. So in our recent work, LLMFusion, we try to merge models across modality. So unlike the prior work that prior multimodal models that is trained end-to-end on combination of text image data from scratch, we propose to reuse existing pre-trained language model like Lava and add a image module on top. So the way it works is we use a Llama model pre-trained for language, and we added a dedicated transformer module for visual understanding and image generation using the modality-specific feedforward layers to process text and image input separately. So basically, if we have a text input, we feed it into the text language models, and you go through this, the attention layer, the feedforward layers. And if we have an image input, we will feed it into the image module. It also has separate like QKV and FFN. And the way the two modules interact with each other is through the self-attention. So basically, the image tokens processed from the image tower, and the text tokens processed from the text tower can attend to each other in every layer. So the merging is kind of very deep across every layers in the transformer model. Is there any question? Oh, Harda?
Yeah, I have a question.
Mhm.
Yeah. Shall I ask now or?
Yeah, sure. Please feel free to ask.
So when you merge two models, does this mean that after pre-training, whatever the weight matrix you get, and merging means I need two components. So one is one weight matrix and another models another weight matrix. So then you, what is the technicalities? Can you tell me to actually do the merging part? Means you are merging the two matrices and the weights component, and then you get a resultant, and that you called as a merged model, because those the resultant matrix have values from the first model and second model to the, what is the core technicalities to do the merging?
Just to make sure I understand the question, so basically, how do we do this kind of merging if we have like two different models?
Yes. Does the merging means weight merging or something else to merge?
Yeah, that's a great question. We are not doing weight merging here. So the way we are merging two modules is by cross attention. So basically, the text token can attend to all the image token here across every layer, and all the image token could attend back to the text module. Sorry, the text tokens. I'll output from the text module. So we are not adding additional parameters. So basically, we have, let's say we have one transformer for image, one transformer for language models, and the way it interact with each other is they can attend to each other's token in every layer. Oh, is this clear?
Yeah, I got it.
Yeah, I think definitely the prior work proposing like way merging for merging different like text-only language model, but I'm not sure it will work in like cross-modality merging because the two models are too different.
Correct. Yeah. Maybe I'll read this, and if I have any question, I'll email you.
Yeah,
for
definitely.
something.
Please feel free to email me. Yeah, thanks for the
Thank you.
question. Yeah, so here's how all it works. Compared with like transfusion, which is a prior model that's trained end-to-end on combination of all data, our proposed approach to LLMFusion could achieve good performance with much less compute. Okay, so this actually wraps the end of part 3. So let's recap what we discussed today. So in this talk, I described some of the fundamental limitations of current monolithic language models, which motivates my research on modularity, trying to build models from composable components to overcome these challenges. So first, I talk about how the model modularity, how we can augment existing language models with external tools like retrievers or visual modules to enhance its factuality or reasoning. And in the last part, I covered data modularity. I think we should build future language models that are inherently modular from decentralized trained components that can be co-developed to ensure data privacy and control. And we can also merge models from different modality to build them more efficiently. Okay, thank you. Is there any question for? Omar, do.
Just a question. I mean, usually what I know is when we're trying to fuse, like, for example, a model that has been trained on images and language model, we try to project the tokens that come from the images using a projection layer so that we have the image tokens projected into the language embedding space. But here it feels like the combination only comes at the self-attention layer. Which you said it's a cross-attention layer. So I don't know how both like methods compare, or if even what I'm saying is accurate or not. I mean, I'm not sure.
Oh, what do you mean by like projecting the image tokens into the text input embeddings? Oh, I think we use a standard tokenization method to tokenize all the image.
Yeah,
so,
I mean, probably I'm wrong, but what I thought is done is there is like a linear projection layer specifically for the tokens of the image. And in a way, the idea is we want those tokens to be projected into the embedding space or the space of the language embeddings. And then the fusing happens like naturally like this.
Are you referring to like image understanding, like clip features? Because they train this
Yeah.
features
It
from
resembles to
that
that.
aligned with the text. So here we're actually focusing on image generation. So for image generation, people usually use this VAE tokenizer. So it's not projected to the text space. We're following the previous model to like the transfusion. We use the exactly same setup.
Okay. So yeah.
Yes,
I thought
so
it was about image understanding more than.
Yeah, I think people usually use different tokenization for image understanding and generation. So for understanding, they have this clip feature, which is which aligns the text and input embedding space. But for the image generation, yeah, I don't think the embedding space is aligned.
Yeah, it makes sense. Probably it would be like aligned in like not into the language subspace, but into the image subspace. I mean differently, if you know what I mean. So it's because the output would be an image.
Yeah, that makes sense. Yeah, I'm not sure if people look into that in image generation setup, but I think it would be very interesting if we can align that to make it better.
Yeah.
I can add a little bit to that as well. I think if we don't have the modality-specific design, if we only have one single tower for video and for image and text, then I think is basically the situation Omar described, because the input embedding of text and the unit sampler of image, like the VAE, would all project to one tower instead of two towers. So that would be like in a single space. Here, like we do modality specific, so it can be considered as two separate space. But we find that the modality specific design is like has a better performance than a single tower.
Okay, I see. Okay, thank you.
Oh, Ahmad?
Yeah, so I had a question as well. So in standard multimodal models, it has been shown in few papers that they are highly biased towards the language model because that is like very highly trained as compared to the vision component. So do you think that if we go towards this direction where we have every expert separately trained, this issue will still occur?
Bias, you mean like a lot of parameters are actually used for modeling language instead of modeling image?
Yeah, and they also use lots of text heuristics as compared to focus on vision.
I see. So here, I think we have like separate power for different modality data. So it kind of makes sure it's like different powers specialize in its own modality. Probably this problem will be mitigated, but I think, like I mentioned in the talk, like the one downside for the standard approach is like, even though, for example, if we just have one set of parameters, then both modality data has to go through all of them. So basically, even for the image tokens, maybe the parameters responsible for image token is only small set, but they still need to go through the entire parameters. But here, if we know, okay, we don't need that many parameters for image component, we can make it much smaller compared with the language model.
Yeah, makes sense.
Yeah, and thanks for the question. I think we're almost at time. And thanks everyone for all the great questions.
Thank you so much.
And thanks so much for the invite.
Yeah, thank you so much. Thank you.
Okay.